In this problem, we can see that we have a graph of the function, and the function appears to be increasing and exponential. Therefore, when we write the equation, we're looking for some y, or I'll call it f of x, is equal to a times b to the x power, which is an exponential function, and b we're going to have as a growth factor. So we expect it to be some value greater than 1. Okay, so using our 2 points here, I'm going to go ahead and write down my 2 points. I've got 2 comma 10 and 4 comma 20. So the first thing that we're going to do is calculate the growth factor. So the growth factor here is going to be b raised to the change in x, so that's 4 minus 2, is equal to the ratio of 20 over 10, okay? And so b to the second power is equal to 2, therefore b is equal to the square root of 2. So now that I have the growth factor, which we check, it is a value greater than 1, then the next thing that we want to do is calculate the initial value a. So to calculate the initial value a, I'm going to substitute in everything that I have into the formula y is equal to a times b to the x. And let's choose one of the 2 points. So I'm just going to choose this first point here, 2 comma 10. So here we can see that when y is 10, don't know what a is, that's what I'm searching for. B is the square root of 2, and x is 2. We can work backwards and solve for a. So let's go ahead and divide both sides by the square root of 2 raised to the second power. So that gives us a is equal to 10. Divide it by the square root of 2 raised to the second power. So a is equal to 5. So now that I have my initial value a and my growth factor b, let's write the equation. So don't forget to actually answer the question by putting all the pieces together. So our equation is y is equal to 5 times the square root of 2 to the x power, and we're good to go. In this particular problem, we're told that a contaminant, strontium-90, decays exponentially at a rate of 3.4% per year. So first thing that we want to make a note to ourselves is decay means that we have a decay factor. So b is going to be a value between 0 and 1. And we have an exponential function. So that means that we're looking for some equation that's in the form of y is equal to a times b to the t, where t represents years. And our decay rate is 3, so R is 3.4%, but always convert your percentage to a decimal correctly, so just divide that percent by 100. And then again, because we have a decay factor here, to calculate that decay factor B, it's always going to be 1 minus R. So our decay factor per year here is 1 minus 0.034 or 0.966. Okay, so notice that we don't know what the initial amount of this contaminant is. So A is the initial amount, but that's okay. We can just call it A, okay, because we just want to know the half-life, which means we want to solve for T, okay, when A becomes half of itself. Okay, so half of A, you can think of that as 0.5A. Okay, so I'm going to put all the pieces together to solve for T. So let's write down everything that we have for this exponential decay function. So let's see here. We want to know what is T when A becomes half of A. All right, and we have a decay factor of 0.966. So hopefully you can see here we have an equation where I can solve for T. So let's go ahead and divide both sides by A. So 0.5A divided by A is going to give me, let me write this down, okay, a half on the left. And now I've got this exponential function on the right, so we can go ahead and take the log or the natural log. So I'm going to take the natural log of both sides of the equation. And we know that anytime we take the natural log, we can apply the power rule. So that's going to bring that exponent down to the front on the right-hand side of the equation. And then now I'm just going to divide both sides by the natural log of 0.966. And that gives me T. So T is equal to this entire quantity on the left. This is the exact solution. Now, if we put this into our calculator, it'll give us an approximate solution of approximately 20.04 years. So the half-life of strontium-90 is 20.04 years. In this question here, we want to write this exponential function y equals 29 times 1.09, and we want to rewrite it in the form of a times e to the kt. So this means I want to write it to show that it has a continuous rate of change. So continuous means that we use that base with the base e, with the irrational number e. So keep in mind that these two equations are equivalent to each other. So I'll write it down here on the bottom. Y is equal to a times b to the t is equivalent to y is equal to a times e to the kt, where the equation on the right-hand side shows exponential growth or decay, depending on what value k is. So if we take a look at these two formulas, we'll see that y is the same in both equations, a is the same in both equations, it's raised to the power of t, that's all the same. And the only difference is that we have b instead of e to the k. So that must mean that b is equal to e to the k. So we can use this equivalence to convert back and forth between the two equations. So let's write down what we know. Well, from the original equation, we know that b is 1.09. And then in the continuous function, we're trying to solve for k. So we want to know what is k. So let's set b equal to e to the k. So I'm going to set b equal to the e to the k, and now we have an equation where we can solve for k. So to solve for k, I'm going to take the natural log of both sides of the equation. This allows me to use the power rule. Okay, so the natural log of 1.09 is equal to k times the natural log of e. We know that the natural log of e is equal to 1, so the natural log of e is equal to 1. This leaves me with, I'm running out of space here, but k is equal to the natural log of 1.09. So go ahead and just put that into your calculator. Natural log of 1.09 is 0.086177, and we want to take this out to 4 decimal places. So this means that k is equal to 0.0862, which is approximately 8.62% continuous. So this is the continuous rate. Okay. All right, question B, indicate whether the exponential function is growing or decaying, and then find the annual and continuous rate. So going back to the original problem here, we know that this function is growing, so we know that we have growth because our factor is 1.09, which is a value greater than 1. And from this growth factor, we can work backwards and solve for r. So we know that b is equal to 1 plus r whenever we have growth. And so I'm going to just substitute b as 1.09. You can see here that we can subtract 1 from both sides and solve for r. And so that is 9% per year. So that's your annual rate. 9% per year is the annual rate. And then the continuous rate, we already found that from part A. So the continuous rate is that rate of 8.62% continuous rate. So you can see here that a continuous rate is always slightly smaller than the annual rate. Okay, we have a word problem here, and we want to write an equation. So here we've got a computer science, from the physics, computer science, and engineering department. They invent a self-replicating robot. At the beginning, they have 6 robots, and then after 7 days, there are 34 robots. So I'm going to go ahead and write the information, the data that's given to us as 2 ordered pairs or 2 points. So at the beginning means when t is 0, we have 6 robots, okay? And so I'll call 6R the number of robots. And then after 7 days, there are, so we'll call this T sub 1 and R sub 1, T sub 2, and R sub 2. So after 7 days, there are 34 robots. Okay, assume that there is linear growth. So linear means I'm looking for some y is equal to some mx plus b, where m is the slope. So the first thing I need to do here is calculate the slope. So the slope here is going to be 34 minus 6 over 7 minus 0. That gives us a slope of 4. Okay, and then we already have the initial value. The initial value here is 6 robots. So that makes us write, this makes the equation easy to write. So that gives us an equation where the number of robots is equal to 4 per day plus an initial start of 6 robots. Okay, all right. Let's see what this equation looks like when we have exponential growth, okay? So if we're pumping out these robots exponentially, what does this equation look like? So an exponential function is always y is equal to some a times b to the t, okay, or to the x. You can think of it as x or t, where that represents the number of days. And again, we know that our function is increasing because notice that as we go from 0 to 7 days, we're increasing the number of robots. And so we expect that b is going to be some number that's going to be greater than 1. So the first thing that we need to do is find that b value. So b over 7 minus 0 is equal to 34 over 6. That's the ratio we use to find the growth factor. So b to the 7 is equal to 34 over 6. I'm not going to even simplify it. I'm just going to leave it like that. And so b is equal to the 7th root of 34 over 6. So that is our growth factor. And again, we know our initial value, a. Here we started off with 6 robots. So let's go ahead and write that equation. R is equal to 6 times the 7th root of 34 over 6 raised to the t power. Okay, so there is our exponential equation. In this part of the question, we want to use the different models to see how many robots we'll have after 3 weeks. So using the linear model, here I want to evaluate R of 3. So let's go back and make sure we understand what T is. So T is given to us as time measured in days. So after 3 weeks, we're looking at 21 days, right? So R of, I should write this as, let me change my notation here. So this should not be R of 3, but it should be R of 21 is equal to 4 times 21 plus 6, okay? So this gives us 90 robots in 3 weeks, okay? All right, let's use the exponential model. So again, 3 weeks is 21 days. So 6 times the 7th root of 34 over 6, raise that to the 21st power. That's going to give us approximately 1,092 robots. So clearly here the exponential model is going to have the robots replicate at and give us a larger output over the same amount of time. All right, using the exponential model, how long? So how long means we're going to solve for t. Will it be until we have 1,000 robots? So already from question D, you can see that after 21 days, all right, we're a little bit over 1,000. So this means we expect t to be some number less than 21, but close to 21. All right, let's set up the equation to solve for t. So I want to know when r is 1,000, increasing at a rate of 6 times the 7th root of 34 over 6. Let's work backwards and solve for t. So the first thing I'm going to do is divide both sides by 6. And then once I have that, I can take the natural log of both sides. So the natural log of 1,000 divided by 6 is equal to t times the natural log of the 7th root of 34 over 6. And then divide both sides by that natural log of 7th root of 34 over 6. So t is equal to the natural log of 1,000 divided by 6 divided by the natural log of the 7th root of 34 divided by 6. So this whole quantity here is the exact solution, but if you put it into your calculator exactly the way you've written it, you will get an approximate solution of 20.65 days, which you can see is slightly less than 21 days as we expected. In this problem, a bank's account is given to us as B equals 12,000 times 1.075 to the T, where T is the number of years since the account was open. How much was the initial investment? That's our A value in the equation. Y is equal to A times B to the T. So we see here that that is an initial amount of $12,000. What is the effective annual interest rate? Okay, so the effective annual interest rate in this particular problem is the value of R in this portion of the equation. So B is equal to 1.075, okay? But we know that because we have growth, that's B is equal to 1 plus R. And we want to know the effective annual rate. So that's when T is 1. So when T is 1, we can see in that portion 1.075 of the equation. If I raise it to the 1 power, it's 1.075, which working backwards gives us a rate of 0.075 or 7.5% annually. So that's your effective annual rate, 7.5%. Now we want to know how much money will be in the account after 3 years. So this is just a matter of figuring out what B of 3 is. So substituting in 3 for T. Let me make sure I didn't write too many zeros there. Okay. 1.075 to the 3. Okay, let's see what that gives us. That equals 14907.56. So that gives us $14,907.56. When will this account balance reach $20,000? So we want to know what is T when B is 20,000. So let's just substitute 20,000 into the equation for B and work backwards and solve for T. So first thing we're going to do here is divide that 12,000 on both sides. Okay. I'm going to just cancel out some zeros here. I'm going to leave that as 20 over 12 and then go ahead and take the natural log on both sides and then apply the power rule at the same time. And so then now T is equal to, divide both sides by the natural log of 1.075. So T is equal to the natural log of 20 divided by 12. Divide all of that by the natural log of 1.075. This is your exact solution. Put it into your calculator the same exact way you see it written down. And this will give us approximately 7.06 years. In these last 3 parts of the question, we want to take a look at what happens if the bank, instead of giving us 7.5% annually, compounded annually, what if we compound it monthly? So question E says, what if 7% was compounded monthly and we make the same initial investment? So same initial investment means A is still 12,000. Okay, but instead of, so again, go back and reference the previous parts of this question. The previous part, we had an effective annual rate of 7.5% annual. Okay, but let's see what happens when we get only 7% compounded monthly. So I'm going to write this formula as C equals, just so that it shows that it's different from the account that is B equals. So here, compounded monthly, we start off with 12,000. Right, but this part of the equation is going to change slightly. We're going to do, instead of 1 plus R, where here R is 7%. So I'm going to rewrite that as a decimal, 0.07. Here we have to take that 0.07 and compound it 12 times because there are 12 months in a year. And we're going to raise it to the number of times we compound it annually times T, because T represents 1 year. So that is what the formula looks like if the 7% was compounded monthly. Okay. Now let's take a look at question F. What is the effective interest rate if we are given that 7% compounded monthly? So to calculate the effective interest rate, what we need to do is actually take 1 and add it to 0.07 divided by 12 and raise it to the 12th power and see what this is equal to, which is 1.07229. So here we can see that the effective rate, so the rate in this problem is 0.07229, which is approximately 7.229%. So here we can see that the effective rate is slightly higher than that nominal rate of 7%. Okay. All right, let's take a look at question G. The bank introduces yet another new account that earns 7%, but notice it's compounded continuously. So anytime you read a problem where it says that your rate is a continuous rate, this means that we're looking for an equation where the base is base E. So this equation here will give us C is equal to, so same initial amount of $12,000, but it's going to be times E raised to the 0.07t. So here our continuous rate is that 7%, okay? And when we convert that to, so you can think of this as K, that's going to be 0.07, and it's going to be positive because we have an account that's growing. If it was an account that was decreasing, then that K value would be negative. All right, but anyway, so just remember that anytime you have a continuous rate or a continuous function, it's always going to be in base E.